All right, so now let me just make some statements about properties of divided differences. Okay, so let me just remind you of the mean value theorem first. All right, so the mean value theorem says that if f of x is continuous and differentiable, then there is a point C such that f prime at C is f of x1 minus f of x0 divided by x1 minus x0 for some C in the interval from x0 to x1, right? So of course, it's like given that we just discussed divided differences, you'll see that this is obviously the first order divided difference. So you might ask whether there's something analogous to this, right? And there is. So the theorem states the following. If f is Cn in the interval from a to b, and x0, x1, all the way up to xn are in this interval and distinct points, then f of x0, x1, all the way up to xn, okay, is fn at some unknown point c divided by n factorial for some c in the interval from a to b. All right. So I should make the following observation, right? Which is that so far it's like we've defined divided differences, you know, for points it's like which are all distinct. And I should then say, well, what happens if some of the points aren't distinct, right? So say some of the points are repeated. Then what you do basically is that when you look at the divided difference table, right, you fill in the part of the divided difference which is repeated. So you basically just, you know, if you imagine all of these were non-distinct, so if you have f, say x0 a bunch of times, right? So say this is n plus 1 times, okay? Then I'm just going to define this divided difference to be the nth derivative at the point x0 divided by n factorial. Okay, so this is for sort of repeated xi's. All right. So if the xi's are repeated, you basically sort of ignore part of the divided difference table, and you only fill in the part of the divided difference table where you have that repeated the appropriate number of times, and then you just fill it in with that unknown value. Okay, so let me try to illustrate that idea. Okay, at least just conceptually. Okay, all right. And then I'll go back to the error estimate. Okay, so imagine you had x0, x0, and x1. Okay, and we have f x0, f x0, and f x1, and you know, I want to do this formal thing where I have f x0, x0, and I can't compute that because that involves dividing by 0, right? But in place of that, let me just write this as the first derivative of f at the point x0 divided by 1 factorial. All right, so the point is that every time you see an entry with repeated x0s, you replace it by the appropriate derivative of f, okay? So so this entry is well defined. I can do this usual divided difference, right? This is just f x0, x1. And then again, I can combine these two in the usual way to give me the divided difference f x0, x0, x1. Okay. All right. So that's just a observation that you can essentially, given the definition of the divided difference and this generalization of the mean value theorem, you can basically substitute. It's like divide the difference entries with repeated entries using the appropriate derivative information instead. Okay, all right. And then with that, we can talk about the error. All right. So the error of fx minus Pn of x, okay, is equal to f n plus first derivative of f at some unknown point divided by n plus 1 factorial x minus x0 all the way up to x minus xn. And with that in mind, it's like I can rewrite this as the following divided difference: f x0, x1, xn, x, and then x minus x0 all the way up to x minus xn. So in any case, so what basically happens then is that this notion of divided differences with the appropriate substitution for what a divided difference means when you have repeated indices then gives you a single unified framework for understanding both Taylor expansions and the associated error terms, right? So with that, you have that Pn of x, right, really is, with this kind of divided difference, right, f of x0 plus f of x0, x1, x minus x0, all the way up to f of x0, x1 to xn, right, x minus x0, all the way up to x minus xn minus 1. Okay, and then the remainder term is this thing, right, f of x0, x1, xn, x, x minus x0, x minus xn. Okay. All right. So again, the bottom line is that with this observation that repeated divided let me rephrase that, divided differences with repeated indices is related to the appropriate derivative, the corresponding derivative of the function at that point. You can then use this notion of divided differences and the associated Newton sort of interpolating polynomial to also incorporate it's like the results we have traditionally from Taylor polynomials. Okay, so that's really quite nice. Okay, so with that, I will stop our discussion of polynomial interpolation, and the next topic will be on piecewise polynomial interpolation or splines. So let me stop here.